Okay, so I think what we were talking about is things like how electric currents can produce magnetism. And so, of course, regular magnets can produce magnetism. So this is like a permanent magnet. But if you have a current flowing in a wire, this also can create a magnetic field. And so you can see it in this picture with the iron filings. And the rule basically that you can use to figure out which direction the magnetic field is going is the so-called right-hand rule. It sort of curls around the direction of the wire. So if you've got your thumb showing the direction of the current, then the magnetic fields curl around like in the direction of your fingers. So magnetic induction is an effect where you can actually create a voltage from a changing magnetic field. So if you have this loop here, you put a magnet inside the loop, then by the time that the magnet is actually being put in the loop, you will get a voltage. And so I think you saw a video about that, where this voltmeter basically it starts to move as soon as you put the magnet in, but only when it's moving, right? And so what this basically tells you is that once there's a changing magnetic field, then there will be a voltage produced in this wire. And actually, a voltage is something which is another way to think about voltage. In the last slide set, I think what we did was to look at the relationship between voltage and the electric field. I think in that case, what we were talking about is that basically voltage was equal to the electric field times by the distance. So basically, if you plotted the voltage with distance, so this is some distance here, then the voltage difference is the sort of the final voltage, and here's the initial voltage. The voltage difference is just the difference between these two. The electric field is actually kind of like the gradient of this. So it's like how quickly the voltage changes, right? So a high electric field will produce a high voltage quickly. So actually, another way to view this is that changing magnetic field will produce a changing electric field. And that's actually going to be the key concept that we're going to need to understand electromagnetic radiation. So, the thing which I want to get across here is that, you really need this time-changing magnetic field. So nothing happens if this magnet is not moving, but then you see something happening when this is moving, which means you really need that time dependence. And so something needs to be changing. Well, the magnetic field needs to be changing in time. Okay. So I hope you did something or talked about something like that in the last lecture. And yeah, okay, so this was the video which I think you were shown, and what this guy is doing is putting a magnet inside this coil, and then this big old voltmeter is swinging when he puts the magnet inside. Okay, and then Lenz's law is sort of like it's kind of like almost the same thing, but it's viewed from the point of view of the magnetic field. So basically what this is saying is that if you've got this kind of coil here and you are, say, in putting this magnet inside, this means that the magnetic field is kind of increasing, right? And so basically what this current loop tries to do is to always try to maintain the magnetic field that is actually there. So before it was small, and now we're kind of introducing this magnet here. And then so basically what this coil does is to try and remove any magnetic field that is being produced, because basically you can think of this inductor as something that it doesn't like change, and specifically it doesn't like changes in magnetic field. Okay, so anytime you change it, it tries to resist it. Okay, so we put this magnet in, it doesn't like it, and so it tries to cancel out the magnetic field that is increasing, right? So say it was 0 before, and then the magnetic field goes up to 10, say Tesla or something, then this coil will actually start to run a current, such as to try to reduce that magnetic field. And if you actually try to take out the magnet after you put it in, now because the magnetic field is going down, it doesn't like that either. It now wants to maintain a magnetic field, so it actually produces a magnetic field in this this direction to the left here, such as to maintain the magnetic field. And this is a similar situation, but with the south poles. And in this case, the magnetic field directions are reversed. Okay. So did you talk about Lenz's law last lecture when Valentin was discussing this?
No, I thought.
Oh, not really. Oh, okay. Okay, sure. Well, let me just show you a video in that case of this kind of thing in action. So, so this is quite a nice experiment. That, let me share the right screen. Sorry, just a minute. Okay. Right. Okay, so what's happening here? So this thing in the middle here is a giant magnet. It's a very, very powerful magnet, the silver one. And this copper ring is just a copper ring. It doesn't have any moving parts or anything like that. It's just you know, a big chunk of a piece of metal, but it's in the ring shape. And what you can see here is that, see this magnet, if you try to drop it through it, it's slowing down, like, you know, like a lot. Like, you know, obviously it's much slower in how it falls compared to if you just dropped it outside of the ring. Yeah, and this is sort of a classic example of Lenz's law, because basically what happens is that in this copper ring here, you know, as you bring the magnet closer, there are currents that are flowing inside this copper, and that is trying to resist the changes in magnetic field. So that, you know, this is a powerful magnet, you're putting it inside, and then so basically the coil is trying to react by producing currents to try to oppose this magnetic field. So this is why it sort of slows down, because it produces a magnetic field that is sort of in the opposite direction of what is you know, being introduced there. Okay, so that's sort of Lenz's law. But the main concept that I want you to get here is that you know, this Lenz's law and then this Faraday's law is kind of very similar in a way. It's just saying that you know, a changing magnetic field produces well, either a voltage or a current or an electric field. Basically, ultimately, all these things are sort of somewhat the same thing. So changing magnetic field produces like a voltage inside a loop. Okay, so that's really the key point that I want you to sort of understand, even if you don't, you know, if you're not familiar with all these, you know, the details of these laws. But I mean, changing magnetic field produces a voltage or an electric field. Okay, so, oh yeah, hi, Bale.
I just have a question. So Faraday's law actually says that the change in magnetic field would induce a voltage or current, and Lenz's law said that the current in the circuit is used to cancel out the outside change of the magnetic field. Is that right?
Yes, that's yeah. Oh, yeah, that's right. So,
All right.
so actually, Lenz's law and Faraday's law are kind of similar, because this minus sign here is kind of the effect of opposing the the magnetic field, actually, right? So this change in magnetic field. So this it says magnetic flux, but basically magnetic flux is just something like the magnetic field times by the area of the loop. So don't worry about the
Okay.
details, but basically this is the changing magnetic field. Right? And then the changing magnetic field produces a voltage. This is basically what Faraday's law is saying. And
Mm-hmm.
Lenz's law is saying something a little bit more like, so just qualitatively, which direction is the current going to flow, right? Okay, so is it going to be like clockwise or is it going to be anti-clockwise? And just depending on that, that will give a different direction of the magnetic field, either the left or the right in this picture. And Lenz's law is just saying that it will go in the direction such as to kind of try to maintain the magnetic field that's kind of there. So it doesn't like any kind of change. And so Lenz's law is kind of a more qualitative, there's no formula to it. It's just kind of like a rule of thumb. And Faraday's law is more like, a bit more like an actual mathematical law where you can calculate the actual voltage. Okay, so I hope that clarifies.
Okay, thank you.
Okay. Okay, so thanks for the question. And all right, so basically a practical electrical device, which is actually used in various circuits, uses this exact effect. Okay, and they're called inductors. And inductors are basically just an electrical component which consists of this coil of a wire. Okay, so here's on the right here just some examples of inductor, and you have just a coil of wire. In this case, this has got some kind of metal going through it. You don't always have to have one. Generally, having this metal in the middle sort of enhances the effect of the inductor. Okay, so it just sort of improves the performance of the inductor, and the main important part is this coil of wire. Okay, and so this is used mainly in sort of AC circuits. So when you have alternating current, and basically what it does, it kind of follows this Faraday's law rule more or less, but it's written a little bit differently. But basically, in this case, it's saying that there's a voltage. A voltage will develop across this coil, this component, and it's dependent upon like the change in the current. Okay, so if the current, say the current was like 10 amps, right, going through here, and then say it changes to 9 amps in like 1 second. Okay, then in that case, this di dt would be something like 1, because 10 it's like 10 minus 9 divided by 1, right? So 10 amps divided by minus 9 amps, and then that happens in 1 second. Okay, and then this L is just some number which characterizes the performance of how strong the inductor is. It's just basically a proportionality constant, so it's just a number. And basically so whatever the L is, I don't know what typical numbers are, but you just calculate this, and then basically it's saying that a voltage will develop across these contacts according to basically this kind of thing. So this is a kind of electrical component which is used in sort of various contexts, which we'll look at. And just so that you sort of get an idea of this, why don't we just do a little kind of demo of this? Maybe so you can follow along, if you like. But let me just go to my version here. So okay, so basically what I've done here is make this kind of circuit. So what have I done here? Well, so this thing here is the, whoops. So this thing here is the inductor, and this is just a resistor. And you don't really need to have a resistor, but if you don't have the resistor and if you just have a wire, I think this thing starts to catch on fire or something like that, or gets very hot, and then yeah. So I think just to have something, yeah. So just to avoid this thing catching fire, I just put a resistor in there, just so that basically the current doesn't get too big. Okay, so you just put a resistor inside here. Oops, what's happening? It's weird. Let me try again. So this resistor I'm putting here. Okay, this thing here is just a battery. Why doesn't this want to connect? Oh, what's this wire? Just some weird thing which I've got here. Oh. Okay, whatever. I'll just get another piece of wire here and connect these things up. Okay, so this is a battery. Okay, so battery obviously just moves the current around, and it's going through this inductor. Okay, and here I've got a switch, right? So what you'll notice is, maybe let's make this a very strong inductor. So what you'll notice is that when you connect it, it takes a little bit of time for this to get going, right? So I'll just do that again, and maybe I'll use a slightly bigger voltage so I can sort of see the effect a little bit more. So you can see it kind of like, it takes a little while to get to the full current, and that is the effect of this inductor here. And these wires I'm not using at the moment, so you can just ignore those. Well, maybe I'll just delete it so that there's no confusion. So in this case, this effect that it kind of goes up sort of slowly to this maximum current is the effect of the inductor. And if you didn't have this inductor, and if you just had a wire, regular wire here, you can see that when I close the switch, it just immediately starts to go at the full current. So the inductor is something that kind of slows the time kind of transition down. So let me just put the inductor back. Okay. So you can see it sort of takes a little bit of time to get going. Okay. Okay. And so what I want to do here is then I want to add another piece of wire here as I had before. Okay, and then I'm going to connect that up. And so what I'm going to do here is, now with this thing running like this, I'm going to like open this switch. Now, when I open this switch, what do you think might happen?
Top circuit will have current.
Right. Yes. Yes, that's exactly right. So let's just try that, and yes, and basically the current will start flowing. Now, so if I didn't have the inductor, and say if I just had a regular wire, like this, right? So say I'm running this, and say if I open it, basically there's no current actually flowing in this. And this is again the effect of the inductor. You can kind of think of it like, it's a bit like something, it's a lot like how, heavy things. So when you have something heavy, extremely heavy, and you try to get it going at a certain speed, when it's very, very heavy, it kind of takes a bit of time to get up to full speed because it's so heavy, right? And then once it's going, it's actually very difficult to stop. It'll sort of keep going, and then, it's difficult to stop. So basically, this is sort of intuitively how sort of inductors kind of work too, because, when you have an inductor, it doesn't want to change the current, right? So let me just put the inductor back there, and, once this is oh, okay, actually, sorry, I need to get this one flowing first. So now when I close this switch, it's going, and then I'll put that wire back. And so over here, like there's a current that's kind of going through the inductor. And when I open this switch, the inductor is like, no, I don't want the current to change. I want the current to just, remain the same value. We can put an ammeter here even. So, here's the current that's flowing through the circuit at the moment. When I open the circuit, what the inductor will want to do is to try to maintain the current at 6 amps, and that's exactly what it does. It just maintains the current at 6 amps, and it will resist that kind of change. Okay, so I hope that gives you a bit of an idea of what inductors do. Any questions? Nope. All right, good. Okay, so let me then go back to my slides again. Okay, so all right, so that's basically intuitively what an inductor does. This whole effect comes from the fact that inductors take advantage of this property that it just does not like the magnetic field to change. And the reason why in the inductor formula over here, it's not magnetic field but current, it's because the current and the magnetic field are sort of related things, right? So if you have a certain amount of current, then a certain magnetic field would be inside here. So if there's 10 amps flowing inside the inductor, then that would produce some number for the magnetic field. And basically it takes advantage of this effect that a magnetic magnetic field changing magnetic field will produce a voltage such as to try to maintain that magnetic field. Okay, so a changing magnetic field produces a voltage or an electric field, and there's a guy called James Clerk Maxwell. He's maybe one of the most famous physicists. And back in the 1800s, he realized that if you write the laws of electromagnetism in this, you can write it in different forms, and this is maybe in terms of physics the way that it's normally written. So Faraday's law, more generally will be written something like this: B is the magnetic field, E is the electric field, and a changing magnetic field will produce a electric field. Okay, and for a long time, people thought that the magnetic field relationship between current, J is the current, and magnetic field was just like this first term on the right hand side here. And this guy James Clerk Maxwell, he realized that actually there's something missing in these equations, and there's also kind of the reverse effect that a changing electric field will actually also produce a magnetic field. So it's just kind of exactly the opposite effect. Instead of a changing magnetic field producing electric field, a changing electric field produces a magnetic field. And it turns out that this term, which sort of he discovered, is kind of like the crucial ingredient to understand how electromagnetic waves and light is an example of electromagnetic wave, how that actually how that works. And so if he didn't discover this term, he was kind of working more on the mathematics of this kind of problem. If he didn't discover this term, then he wouldn't have figured out how light actually behaves. Okay, so so basically, basically how this whole thing works is that normally when you have an electric field, what you kind of think of is that you have, say, a charge, and then there's some electric fields going out from the electric field, right? And similarly, if you've got a current, so say you've got a coil of wire like this, and got a battery maybe, then using the right hand rule, you can work out that the magnetic fields are, kind of go around somewhere like this. So, without, this kind of looks like, you only get electric fields when you have a charge, and you only get a magnetic field if you've got a current, right? But what's interesting about these electromagnetic waves is that even though you have like no charge, or current, you got no current, no charge, yet you can actually still have a electric or magnetic field. And this sort of looks almost impossible because, you sort of think of these electric fields, well, surely they come from somewhere. But when you have an electromagnetic field, it's very interesting that you can actually have an electric and magnetic field, and there's no charges or there's no currents anywhere around. And the great trick of how this can possibly happen are exactly these terms which I was sort of going on about over here. So basically, if you have a changing magnetic field, it will produce a electric field. And then if you have a changing electric field, it can produce a magnetic field. And so basically, the magnetic field produces the electric field, and then the electric field produces the magnetic field, and then the magnetic field produces the electric field, and then this just sort of keeps on going on. And then it actually doesn't require any charges or currents at all, and you can actually have this sort of self-sustaining sort of oscillation between magnetic and electric fields. And this is actually what light actually is. It's actually this kind of effect where electric fields and magnetic fields kind of produce each other, and we don't even need any charges or currents or anything nearby. It can just sort of self kind of propagate and create each other, and then just fly off. And this is actually what light actually is. So that was the great sort of discovery that Maxwell made. So electromagnetic wave kind of looks like this. It's actually this blue one is the magnetic field. So the magnetic field kind of oscillates, and then the electric field also oscillates, and they're kind of perpendicular to each other. And basically one sort of creates the other. So that means that when one is large, then the other one should be small. It's actually not how it looks like in this picture. I wonder if this picture is wrong. So what I kind of expect, and maybe anybody if anybody knows the answer, maybe you can tell me. So what my understanding was that the energy should actually go between the electric field and the magnetic field. So it's sort of like a like a pendulum, where the energy actually oscillates between the magnetic and the electric. So when one is high, one is low, and one is low, one is high, and like this. Now, what this picture kind of looks like is that it's actually, they're both high at the same time. And so that actually doesn't quite make sense to me, but okay, I don't know. I'm not sure why that is. I'll have to think about that. Maybe this picture is wrong, or maybe there's something which I'm not quite understanding, but yeah. Okay, so I don't know about the this exact picture, but for sure the magnetic field should be in this perpendicular direction to the electric fields, and then they basically propagate in this direction, which is orthogonal to both. All right. Okay, and then this is just this is just sort of a T-shirt that is often seen around physics departments in the world. So, I mean, it actually is, kind of quite profound, because if you think of, well, what is light? I mean, when before, in the days when people, didn't really understand what light is, it seems like this completely different type of, who knows sort of what it is. Is it a particle? Is it a new type of, so like an atom? What is it made of? But basically to link all these things into saying that, actually electric fields and magnetic fields, when they become sort of interlinked through this electromagnetic field, so if you have these fundamental laws of electromagnetism, then from there you can actually derive, what actually light really is. And so this is just a little, kind of physics joke, if you like. So, and God said, these are the fundamental laws of electromagnetism, and then there was light. Okay, so yeah, so you can of course have many different types of frequencies of light or electromagnetic radiation. So this goes anywhere between, the visible wavelengths that we can see with our own eyes, all the way to, infrared radiation, microwaves, radio waves, and in the other direction towards the shorter wavelengths, ultraviolet rays gives you suntan, and then the shorter wavelengths tend to be these rather dangerous types of radiation, because they can actually harm, they're harmful to the human body. So things like, well, X-rays, so long that the doses are not so high, of course we use them to see inside our bodies, but gamma rays are even shorter wavelength electromagnetic radiation that comes from radioactive decay, and those are quite harmful to the body. And well, X-rays also, you don't want to have too many X-rays per year, because it's also damaging in large doses. But generally speaking, these ones with the shorter wavelengths tend to be more and more dangerous to the human body, and then the longer wavelengths are less dangerous. Okay, so this basically is just talking about the the wavelength of these waves here. So the speed of these waves are always set to the speed of light, which is 3 times 10 to the power of 8 meters per second. But then you can have different frequencies and therefore different wavelengths according to just the wave law, which is C equals F lambda. So the frequency, this C is the speed of light, and then F is frequency, and then lambda is the wavelength. Okay. I didn't really sort of derive anything to show you how electromagnetic waves, can exist. So if this was like a more detailed physics course, then what we'd be doing is to sort of start with these equations here, these bottom 2 equations, this is the electric field related to the magnetic field, and this is the magnetic field related to the electric field. And then, from those, we can actually derive that you can have wave-like solutions that eventually look something like this. So you should be able to derive that. But sort of in practice, how do you actually make these electromagnetic waves? And There are many ways to make this, but actually there's a kind of maybe a central concept in sort of engineering and physics where you can actually make electromagnetic waves by accelerating charges. And there's a video here which kind of explains this quite well. So let me show you that. Share the right screen first.
Was a clear case of electromagnetic wave propagation and detection. However, before Hertz, the brilliant mathematician James Clerk Maxwell had already laid out the foundations for electromagnetic radiation by formulating 4 mathematical equations. However, these equations and the Hertz experiment raised the question: how do electromagnetic fields detach themselves from wires and propagate through a space? More specifically, what we need is a traveling electromagnetic wave and not a fluctuating one. Let's explore this logically. Consider an electric charge, which is moving at a constant speed. The electric field around it is shown. Now, imagine for a fraction of a second, it accelerates. After that, it continues its uniform motion at a higher speed. What we need to understand is the effect of this acceleration on the electric field. The interesting thing is that the information does not travel at an infinite speed. Instead, it travels at the speed of light. Similarly, the information about the sudden variation of velocity of the charge does not get conveyed to the whole electric field region. The field near it knows about it, but the field far away still has no idea that the charge has accelerated and it is still in the old state. Let's separate out these regions with the help of 2 circles. Since the electric field cannot break, the field between these distances must transition. This transition field is known as a kink. The kink moves or radiates outwards at the speed of light. To show the kink animation in a clear way, let's move the camera along with the charge. We can say here that the acceleration of the charge has caused an electromagnetic disturbance or electromagnetic radiation. Based on this understanding, we will be able to understand the most important experiment in the field of antenna technology, the oscillating electric dipole. The interesting fact about this simple oscillating dipole is that it produces electromagnetic radiation in a perfectly sinusoidal manner. Let's see how it is achieved. Before getting into the electromagnetics, let's understand how velocity and acceleration vary in this simple case. It is clear that at both ends, the velocities should be 0, and in the middle, the velocity should be at the maximum. This means that this is a case of continuous acceleration and deceleration. The electric field pattern is drawn here when the charges are far apart and when the velocity is 0. In order to have a better understanding, let's examine one of the electric field lines. Let's observe the electric field line at t by 8. You can see that the electric field line is deformed. The reason for this deformation is simple. This time period is the region with the highest acceleration. As we saw earlier, accelerating or decelerating charges cause kinks in the electric field. In short, the old electric field does not get adjusted to the new field very well. This deformation is continuous since there is continuous acceleration in the charge. When 2 charges meet at the central point, the deformed line also meets there. After that, it detaches and radiates. This radiation travels at the speed of light. If you plot an electric field intensity variation with respect to length, you can see that the radiation we have produced is perfectly sinusoidal in nature. Please note that this varying electric field will automatically generate a varying magnetic field perpendicular to it. Now, let's have a look at how this applies to an antenna. A time-varying voltage is applied to the metal wire as shown. Due to the effect of the voltage, the electrons will be displaced from right to left and create positive and negative charges. With a continuous variation of voltage, the positive and negative charges will shuttle back and forth in the wire. This simple arrangement is known as a dipole antenna. The dipole antenna produces the same radiation as we saw in the previous section. In this case, the antenna works as a transmitter. The frequency of the transmitted signal will be the same as the frequency of the applied voltage signal. The same antenna can act as a receiver if the operation of the antenna is reversed. When propagating electromagnetic waves strike the antenna, the oscillating fields of waves create positive and negative charges at the ends of the antenna. The varying charge accumulation means a varying voltage signal is produced at the center of the antenna. This voltage signal is the output when the antenna works as a receiver. We can note here that for perfect transmission or reception, the length of the antenna should be half of the wavelength. This is the first antenna design criterion for proper reception or transmission. The second most important design criterion is a term called impedance matching. Perfect impedance matching will make sure that the waves are radiated in the most efficient way. When an alternating current passes through a circuit, it faces opposition from the combined effects of resistance, inductance, and capacitance. This combined effect is known as impedance. According to the maximum power transfer theorem, to transfer the maximum amount of power, the load impedance should match with the source impedance. For further understanding, let's take an example of a circuit containing an alternator as a source and a motor, bulb, etc. as a.
Okay, so all right, so let me just go back to the slides. So basically, the key idea here is that in order to make these electromagnetic waves, you need to have a accelerating charge. Okay, and so in the video, what we saw was that we had a simpler example where we had an electron that had initially let me just borrow the graphics there, right? So here what we had was basically, okay, so I'm not sharing the right screen. All right, so here we've got, actually it's a positively charged particle, and the electric fields all go out in, radiating out in all directions, right? And now basically when you accelerate the charge, then what happens is that any kind of change in the electric field, and because you're accelerating it, there will be a sort of a change in the distribution of this electric field, right? And because this change actually moves at the speed of light, so outside here, you can work out that, say you suddenly changed the position of this charge. Now, outside basically the circle, it's because this any kind of change in the electric field can only travel maximum at the speed of light. So outside the circle really has to be the same distribution of the electric field, but then inside the circle it needs to be a different distribution, and this basically produces a kind of a kink in this electric field, and this kink is basically what actually kind of propagates out. So it actually so you can see here that the kink actually starts to move out radiating out. And so this kind of principle is the real basic effect of what we're trying to take advantage of when we are trying to produce a electromagnetic field. And practically what is a slightly nicer way to do it is to actually just have charges which are oscillating back and forth with a sine kind of shape. Okay. And you could do this with just one charge, but actually you could also do it with two charges, plus and minus. This is actually a little bit more easy to make because when you have a voltage, you'll have a plus and a minus terminal, and so it's natural that you have like a plus and a minus charge, right? And so the plus and minus charges sort of move back and forth, and this actually again, because the charges are accelerating, it produces this kink, and eventually this kink is actually what radiates out. And so this is basically how you can actually produce a electromagnetic field. Any questions at this point? No? Okay. Okay, and we actually, well, the video also described how antenna actually work as well. And so antenna are just basically, well, the antenna can actually play two roles. It can actually produce the electromagnetic field. And so we can think of this as like radio waves or some kind of wave like this. Or it could actually receive them. Okay, and so maybe initially we can just think of it as producing the field, but basically it's just a piece of wire that has a alternating current that's kind of placed across it. Okay, so we have basically this kind of two sort of wires that are in sort of opposite directions, and if you have a alternating voltage, then basically at any given time you'll have like plus charges or minus charges, and then a moment later it will reverse, and so you'll have this sort of, again, this dipole, oscillating dipole kind of configuration. Yeah, Owen.
Yeah, sorry, are you sharing the YouTube video?
Oh, sorry. No, I'm sorry about that. Now I'm sharing the slides. Yeah, sorry.
Yeah, I can see it now.
Yeah, okay. Okay, yeah, sorry. I was saying that the dipole antenna is basically a simple way of producing the electromagnetic fields. And this basically works by having these two pieces of wire, which have a alternating current put across it. And so at a particular instant of time, you'll have these positive and negative charges over here, but then the next instant, they'll exchange places. So this will be negative, this will be positive, and then the next moment, this will be plus, this will be minus. And so this will sort of go back and forth like this. And so if you have a piece of wire where you have like the charges going back and forth like this, and we saw the example of that. Maybe I'll just point it out again. So you can kind of see here. So you notice here that, see here, these blue dots are the electrons, and the pluses here are the sort of the lack of electrons, right? Because if you have a conductor and the electrons are taken away, then it'll be positively charged, right? So basically what happens in the antenna, if you're producing the electromagnetic field, is that these electrons are kind of going back and forth. So now it's over here. Well, okay, so I think you could see it, but so now it's at the top here, but they all go down to the bottom here, and then the next cycle it will all go back, and then it'll be at the top here again. Okay, and so basically that accelerating charges actually produces the electromagnetic field. This is just another. Okay. So this is just another configuration of the antenna. So sometimes actually you don't even have to have you can have another half antenna. So this is instead of having two wires, you can actually just have one wire. Maybe I'll just skip explaining this one because it requires a little bit more knowledge of electromagnetism. But basically, if you've got a piece of metal here and a piece of wire like this, then there's this thing called the so-called image charge, and charges in this metal actually rearrange themselves to effectively produce the opposite charge over here. So you can actually cut down the size of the antenna using this little trick. Okay, but let's maybe not worry about that too much. So so actually this is how radios work. Okay, so essentially what you have in a radio is you've got your transmitting antenna, and you've got this transmitter, and so you've got some piece of wire going up, some tower usually, right? And basically you just produce these oscillating charges inside the antenna, and by producing these oscillating charges, this actually creates electromagnetic waves. And the electromagnetic waves are now, not bound to the electrons in the wire anymore. They can just fly off, right? Because they can sort of self-propagate, and the electric field produces a magnetic field, and they're kind of like they just shoot off into all directions. And so the radio waves here would radiate out from the antenna, and what happens when you have your receiving radio is that these electromagnetic fields actually make the electrons inside an antenna actually oscillate, okay? And they oscillate at the same kind of frequency as the electromagnetic field that's created. And by kind of, looking at the current, you can actually, well, this is the basic principle of making a radio. So in principle, this kind of works, but the problem is that the signal might be like super weak. Okay, so the actual current that you have inside this antenna might be extremely weak, and you might not, have very much of a signal in the receiver. But but this is basically how radios work, and eventually we'll see that this is also how your mobile phones work. This is how you transmit information. Ultimately, any kind of wireless technology is basically using some kind of variation of this kind of idea. Okay, so how can we improve on this particular design? So we can improve on this design. As I was saying, what you get in the signal here is actually very, very weak. Okay, so how you can improve on this is by doing something like what we do with sound. So if any of you guys play guitar, you'll know that you basically have something that is making the sound in the first place. So in this case, it's the guitar strings. And then you have the body of the guitar. And if you didn't have the body of the guitar, the sound would be really very, very, wouldn't be very loud at all. Like you couldn't hear it very well. The role of this oscillator, well, the body of the guitar is to act as an oscillator. And basically this just sort of amplifies the waves, because you have sort of the source of the sound here, and you have basically the body of this guitar, and by the strings vibrating, it actually makes this whole, like all the air inside the guitar body also oscillate at that same frequency. So you're playing some notes here, and all the air inside the guitar actually oscillates at that frequency, and that actually amplifies the waves a lot. So using the same kind of trick, we can actually improve the performance of this radio a lot. Okay, and so the basic thing that we're going to be using is a so-called tank circuit, or LC circuit. And basically what a tank circuit is it's a combination of this inductor and a capacitor. And as you can kind of see, but we'll just make a little circuit on our online demo thing in a minute. But basically what happens is that this kind of circuit has a natural kind of oscillation to it. So you can see that this current is actually oscillating, forwards and backwards. And so it's a natural kind of oscillator which works for electrical circuits. So so what is a capacitor? Maybe some of you guys know this, but basically a capacitor is, so a tank circuit, LC circuit. This L means an inductor, and the C means capacitor. And so it's a combination of an inductor, which we already talked about today, and then a capacitor, and just connect them by 2 wires. So a capacitor is basically like a small sort of rechargeable battery. And how it basically works is that you have 2 electrical conductors separated by some small distance, and they are not connected at all. Okay, so there's an insulator in between them, and the reason why a capacitor acts sort of as a battery, if you like, is that when you charge up the capacitor, you will have some charge here on, say, the positive plate and some charge here on the negative plate. Now you could take away this battery, and these charges will kind of want to stay there because the opposite charges attract, right? So normally, like the positive charges here might, just drift away somewhere because, the positive charges don't really want to be near each other, right? But because it's feeling the effect of this negative charge, the charges on the capacitor kind of want to stay there because it's near the negative charge. Okay, and so the capacitor has the effect of kind of storing some charge on its plates like this. Okay, so yeah, so the way that the energy is actually stored is, these capacitor and an inductor are quite kind of similar devices in a way, even though they don't look very similar. But basically, one is sort of playing, one is storing energy inside the electric field. So here, if you've got a charged capacitor, then you'll have electric fields between the plates. And actually the electric field, the energy inside electric field is something like the electric field squared. Okay? So the electric field stores the energy by creating an electric field. Sorry, what did I just say there? The capacitor stores energy by storing the energy in an electric field. Meanwhile, the inductor actually stores energy in its magnetic field, and the magnetic field is actually threading the middle of this coil here. So the magnetic field sort of looks something like this. So they're going around through the middle of the inductor and then out around the outside. So this always has some magnetic field, and the energy stored inside the magnetic field is actually also a very similar formula, half mu b squared. This one is half epsilon b squared, and epsilon and mu are just some numbers that basically tell you they're dependent upon the material that's inside the capacitor. So this one has some iron kind of bar inside. A capacitor usually actually also has some kind of material inside there, and so just depending on the material, different values of these things, but they're basically just some kind of constants. Okay, so they're actually kind of very analogous types of things. One is sort of an electric field storage kind of device, and another one is a sort of a magnetic field storage device. And when you combine such things, then you get this LC circuit, and maybe we can just do that and then finish up for today. So so if you've got an LC circuit, so hold on. So we can let's try and make this particular circuit here. So this is my old one. So let's get rid of it. We're going to make an LC circuit here. How do I get rid of this thing? Oh. Okay. Okay, so we'll need a battery. And so firstly, we'll need to get a capacitor. And we're going to join capacitor like this. I'm going to put a switch here. And what this is going to do is this is going to charge up the capacitor when I flick that switch there. So you can see the charges actually develop on the capacitor when I flick that switch there. It's a bit hard to see. Maybe I can zoom in. No, I can't. But I think on one of these plates, there's negative charge that's developed on the capacitor, and one of these positive charges developed on the capacitor. So this is a charged capacitor. I can discharge the capacitor just by adding some wires here, and what you should see here now is that the capacitor will actually discharge. Okay, so now there's no current. Okay, maybe I should have opened this one. So now there's no more charge on there, but if I flick the switch, then this will charge up the capacitor. Okay, now let's add an inductor here. And oops, let's open that switch. That was just to charge the capacitor. And you can see basically what the effect of this LC circuit is, which is to it sort of oscillates the charges back and forth between these plates. So now this is positively charged on the left, and then now it'll be negatively charged. And the reason why it does this is that basically, you know, an inductor is always trying to kind of maintain the same current that's going through here, right? But on the other hand, basically, it can't keep on doing this forever, because at some point so much charge builds up on these plates so that, you know, no more charge can actually go onto these plates. And then so it basically has to stop at some point, reverse direction, and then go the other way, because there's so much charge, electrons that have developed on this plate of the capacitor, that it basically has to sort of go the other way. And then once it starts flowing in this direction, the inductor tries to maintain that, and it tries to keep on going. But then at some point, the capacitor stops it, and then the capacitor tries to get rid of its charge, and then the inductor is you know, trying to stop the change in the current. And so basically, this cycle just kind of continues on forever and ever. And so basically, an LC circuit, or this tank circuit, something that basically has this sort of natural oscillation frequency for the electrical circuit. Okay. Right. Maybe, I think maybe that's a good time to sort of finish up. Wait a minute. Sorry. Yeah. So yeah, I think maybe we can leave it there, and then we can talk a little bit more about how radios work and things like that in the next lecture. So, any questions on the stuff we did today? Okay, no, then I will see you next week. And as usual, homework is just to summarize what we've done this week. So please hand that in on Brightspace, and well, see you next week.
Thank you.
Thank you.